All right, so let's talk about encapsulation and class invariants, right? These are two topics. The first topic, we're going to look at, we're going to revisit abstraction. We have been selling you the idea that abstraction is good, and in general it is. But we'll consider examples where perhaps taking it a little bit too far can be counterproductive, right? And then we'll look at class invariants on saying how do we identify things that we need to know that they are true, some statement, some logical statement, and how do we make sure that that is the fact that our class is enforcing these invariances. All right, so let's revisit representing or models how to represent a certain piece of data, right? So, back when we looked at ConnectNModel, right? There's in an earlier lecture, we talked about how to represent a tic-tac-toe board, right? And how to represent something a little more general, using the Connect4 game, right? And how is it that you represent a board and validate that that you have indeed connected 4 tokens. We try to generalize that to ConnectN, right, where we can configure a game where we can a more generic game. We can say, well, we can have connect any number of tokens, right? Not just 4, but let's just what if we want to be 6 or 7 or whatnot. So the interface that we had considered might have looked something like this, right? Where we have a enumerated data type, a status variable that allowed us to identify what the current state of the game, right? Whether you are playing, whether it was completed, right, and somebody won, or whether there was a stalemate, right? Those were the 3 particular states that the system could be in, right? And we decided to represent them as enumerated data type as opposed to strings or integers, whatnot, right? We also provided a couple of functions or methods that allowed anyone implementing this game to any client using this game to be able to determine the current status, and to be able to determine whether it's over, who the next player was, identify who the winner was, and also identify which token was where, right, in a particular position, so that it could be used for rendering the board, all right? So this was the interface. So let's take a look at a simple implementation, and how would you model this, and then try to apply some abstraction principles that we have been for the last couple of weeks, yes, or a week or so, and see how far that takes us. Right? A particular implementation. I'm sorry. This is right. So this was part of the interface. There were a couple of things. There was also methods that will allow us to mutate the state, right? To move a particular token from one location to another location, right? And also who was doing the movement. Also allowed us to retrieve some configuration about the game, how big it was, the width and the height, how many players there were, how many connects did you have to connect to win the game? Yes. Also, allow us to query the data model and say, is a particular column full so that you can't move into that column. So this was the interface that we considered in the ConnectNModel interface. Yes. All right. So let's take a look at an implementation, a really trivial implementation. Mostly, we're going to be focusing on the data that we want to capture, right, and how to represent it and how to use the interface for that model. Right. We're not going to actually implement any of the algorithm of moving things around and how to calculate whether you want or not. That's not the point, right? What we're going to focus on is mostly on the model, the data, and then applying abstractions to that representations over and over and over until the model becomes meaningless, right? Until there says, wait a minute, I think maybe I abstracted my way into oblivion. So yeah, so let's talk about the type of data that we need to capture, so that we can support and implement that interface. Certainly, the grid is rectangular. Perhaps we might choose to use some kind of array, or maybe a sequence of numbers or sequence of integers, or maybe like a sequence of integers, like an array of arrays, or list of lists, or array list of array lists, to create a two-dimensional grid, and then place the different tokens, whether it's an integer or whatnot, into that grid, and whether we fill that location into that grid. Yeah, we need some ways of representing the size of the board. We need ways of representing this grid as a sequence. So we know that certain values are going to be are not going to be mutable, meaning they're going to be set at the beginning and they're not going to change after that, right? This is going to be like the configuration, the initial configuration of the game. The size of the board, the width and the height is going to be set perhaps in the constructor, and then it's not going to change ever again. So those are fine to be finals, right? Also, how many players are playing? Presumably 2, 3, 4. Also, how many do you need to connect to win the game? Is also a configuration. It's a property, initial property of the system. So they're fine to be declared as final, right? And presumably the constructor will initialize this, and then these will never change after that. Right? So that seems a pretty safe bet. For the grid, right? There's several options that we might choose. It could be a two-dimensional array. It could be a list of lists, right? It's pretty arbitrary what we choose, as long as we can operate on it. Since a list on list seems to be the better option, since we can use one of the indices to iterate over the columns, and then we can use the second index to iterate over the rows, right? And it's easier if we have columns containing rows, so that we can easily look at the list of the length of a particular column, right, and very quickly determine whether it's already full, right? Just by looking at the length, we can determine and says, ooh, this column is full. I can't move into that column, right? So because we're thinking ahead of some of the operations and how it might simplify our implementation, a list of lists seems to be a particularly convenient way. Yes, but really it's arbitrary. Any particular implementation will do. Just that a column of rows it seems to be more convenient because of some of the operations of calculating the length of those columns. So there it is. So we chose arbitrarily again. We chose that we're going to keep track of columns, and the columns are going to be a two-dimensional container, collection of collections, right? A list of lists of integers, right? And then we've decided to represent players as integers, perhaps with a token that represents one player or a different player, right? Zeros and ones, or twos and threes, or whatever token you decide to represent that player. Status. The status are these are mutable, right? Yes. No, there was a more general version of that where we looked at Connect4 and then we generalized that on ConnectN. I think we covered that earlier. Yeah. So it's ConnectN. Yeah. And so we're going to try to go a little further, right? We went from tic-tac-toe to Connect4 to ConnectN, so we're making it more and more generic, and it seems like we're a good place right now, right, of abstraction, but we're going to keep going in the abstraction game, right? And we're going to end up purposefully, right? We're going to end up in taking abstraction a little bit too far, right? And those are all design choices. Right, of how far do you want to take this, right, in the abstraction game. Right, so unlike the width, the height, the goal, the how many players and whatnot, right, those are all configurations at the beginning, and those are final. They don't change over time, as opposed to these over here, the statuses and the current turn of who's currently playing. these are mutable, right? These change over time, right? It's my turn, then your turn, then my turn, and so on and so forth. And the status, it will be, well, when in the middle of playing the game. At some point, I'm going to either, somebody's going to win, or it's going to be a stalemate. Yes? All right, so those states change over time as the game progresses. So these are not final, right? They're just variables that will change over time. So that looks also a pretty good bet. So this is what we have so far, right? Our model consists of a couple of four immutable constants that are going to be set up at the beginning of the game, right? That's kind of like the configuration or the properties of the game, and don't change over time. We have a couple of variables that keep track of the current state of the application of the game, right? Whose turn it is, what current status am I in, and also the position of the different tokens on the board, right? Which is a collection of collections here, right? So these three variables, right? The columns, the turn, and the status keep track of the state of the application. Yes.
Why is it final, the columns?
Oops, I guess not. The no, it cannot be final, right? We need to change over time. Yeah.
So you change the third is final. If you have a data structure that contains other data structures and you declare like top data structure as a final variable, does that?
Oh, the internals.
Anything in the internal?
No, the internals can change over time.
So
the outer one,
could be
Yeah.
not changing the number.
You can't change the size of the grid once you set it. The values, yes, but not the structure. Yeah. So this is the model that we have so far, right? Of the variables, the constants, and whatnot. And it looks like it's a pretty good description of the game, of the current state and whatnot. Looks like a nice abstraction layer that has meaning, right? We read each one of these variables, and they have some semantics behind it, right? We look at each one of these variables, and it clearly tells us and describes. Even the naming is good, right? It gives us a theme of what each one of these things do. So all right, so let's start abstracting, right? Let's start abstracting a little bit, right? Let's go one level of abstraction inwards.